So I got here and realized that my tripod is broken. So you might have to, hopefully you'll be able to zoom in on this. So what we're doing today is we're starting chapter 6. And chapter 6 is about exponential growth and decay and about logarithms. So we're going to start with a quick review of what you learned in Algebra 1. So in Algebra 1 you learned about exponential growth and decay. Right, so by exponential what we mean is that the variable in the equation is the exponent itself. Right, so not like a polynomial, right? It's like the actual exponent is the variable. So here we can use this to look at whether or not, right, when things are either growing exponentially by gaining in whatever our y value is, in this case it's money, or when it's decreasing, right, when the y value is decreasing. So let's say I have a painting, right, and the value of the painting is our y variable. Here's our model, right here, and t is the amount of time that has gone by since its initial appraisal. So what I'm going to do is I'm going to look at this equation, and this number right in front is the starting value. So in part B, when they ask me what's the original value of the painting, well, I'm going to say that's $350. Sorry, I'm going out of order here. This number right here, we call the growth, or we'll call it the growth factor. When this number is greater than 1, it's exponential growth. And if it's less than 1, between 0 and 1, we'll call it, you usually call it B in the equation, then that's decay. So let's look at this number right here. This number is greater than 1, so this is growth. And by the growth factor, we mean whatever's being raised to the exponent, the variable exponent. Okay, so if I want to know the value of the painting in 10 years, well, that means I know t is 10. So I'm going to plug in t is 10, and definitely you want a calculator in this unit. You can enter that right into your calculator. And we're going to get approximately $518.09. So that's how much our painting that was initially $350 will be worth in 10 years. Now, a really common use for this type of information, this exponential growth, is in financial settings. So this is a formula that maybe you have seen. Now, I'm not going to go too much into this because of interest and time, but P in this case stands for the principal, which is the starting value. That's the number 1. This is the interest rate. N is the number of times the interest compounds per year. And then that's N right here. And then T is time. So let's see this in use. I have a $4,000 investment that pays into an account that pays 2.2% annual interest compounded monthly. How much will the investment be worth after 8 years? Okay, so let's see what this is. Our principal in this case is our starting investment. So that's going to be $4,000. So I'm just going to put the pieces in here. Now they say that my interest rate is 2.2%, but remember 2.2% means divided by 100. So 2.2% is 2.2 divided by 100, which turns out to be 0.022. If something's compounded monthly, that means it's compounded 12 times per year, right? Because there's 12 months in a year. So that's going to be 12. And then it says we're going to leave it in there for 8 years. Right? So here, I might want to put this as 96 in my calculator, 12 times 8. And if I punch that into my calculator, my $4,000 investment is going to be worth $4,768.98 after 8 years. Right? So this formula we use when we have a specific number of times our interest is compounded per year. I'm doing this one because we're actually going to do one with continuous compounding, which is slightly different. So this, if this is like a foreign language to you, you might want to go back and watch some videos, like Khan Academy videos about exponential growth and decay, because this is all Algebra 1 material. Or you can come see me at tutorial and I can get you a kind of crash course on it. Okay, what we're interested in is specific case of exponential growth and decay. And that is when the base of the exponential function is e. Now, e is a little bit confusing because when we think of a letter, we usually think of a variable. However, e is actually not a variable. It's an irrational number like pi. Like we know pi is equal to 3.14, et cetera, et cetera, et cetera, right? So it's not a variable. It's actually an irrational number that's value is approximately 2.71828 ... just like pi, right? Lots of numbers that go on forever. So because it's a base in an exponential function often, we can use the same exponent rules that we always use when we use x's or other numbers. So here, if I have something like e to the third times e to the sixth, we remember from our lesson today on 5.5 that we're going to add the exponents and keep the base the same. So if I want to do e to the third times e to the sixth, that's e to the 3 plus 6, which is e to the 9th. Right? So I'm going to do the same exact thing as I do if that were an x. Same thing here. When we divide, we're going to subtract the exponents and keep the base the same. Sorry, my writing is slower because of my hand. Okay, so of course these I'm just going to reduce. 16 over 4, that's 4. And then I'm going to subtract the exponents. So that just gives me 4e to the first, which is just 4e. Right, and that's an irrational number, right? That's not a variable at e. Okay, now we're going to throw a variable in. Right, here I'm going to multiply the exponents because I'm raising a power to another power. Right, but I have to remember I have to raise the 2 to the third as well. So that's going to give me 8, because 2 to the third, right? And then e to the 5x times 3. So that's going to give me 8e to the 15x. So those are applying the 3 rules that we know and love from our exponent life. So anyone curious about what a graph of an exponential function with base e looks like? Well, here we are. In general, right here, notice I've got my a, which is my starting value, and then this time my exponent is, right, I've got some sort of rate of growth or decay, and then I have a variable x. Notice e is the base to which x is raised. That's how we know it's an exponential function. This is the variable right here, right? That's the base. E is the base, sorry, and x is the variable, right? So when e is the base, we call it a natural base exponential function. So it's a little different than the review we did up there in terms of determining whether it's growth or decay. So when my A is, we're only going to look at situations where A is greater than 0, right? Our initial starting value, because we're looking at applications where it doesn't make sense to have a negative A value if we're looking at application. So when R is greater than 0, this R right here, we know that it's a growth function. And when R is less than 0, right? So if that's a negative, if R is negative, we know it's a decay function. So in general, if you guys remember from Algebra 1, exponential functions look like swoops, right? Kind of like roller coaster swoop. So if I have a positive, this is e to the x, if I have a positive growth factor here, that's a 1 there, right? My R is 1, and my A is 1, right? I can assume it's going to swoop up from left to right, right? That's what a growth function looks like. A decay function, on the other hand, this would be a negative 1 for R and a positive 1 for A. So here it's going to swoop down from left to right. And that's something that when you graphed exponential functions in Algebra 1, you notice the same pattern. Growth, swoop up, decay, swoop down. So all of this is so theoretical. Let's actually do a graph. Okay. So we've got y equals 3e to the x. Okay, so there's nothing in there for r, so I'm just going to put a 1 in there. Right, so I know here that r is equal to 1 and a is equal to 3. So since r is greater than 0, I'm going to be able to say that that's growth. Right, and I know because r is greater than 0. That's how I know it's growth. Okay, so the way I'm going to graph this is just the old-fashioned plug-and-chug way. Okay, so the reason I have y exact and y approximate is the exact values are going to have the e's in them, right? And the approximate values, we're just going to punch it in our calculator and do an estimation because it's easier to graph when there's an actual number to graph. So here are the x values we're going to use. So let's plug in ex is negative 2. Right? So if I plug in x as negative 2, I get 3e to the negative 2. So you can just punch that into your calculator. And if you punch that into your calculator, you get approximately 0.4. So that means the point negative 2 comma 0.4 is on our graph. So let's just put it right about there. Okay, let's plug in negative 1 for for x, sorry. That gets me 3e to the negative first. And if I just punch that in my calculator, I get 1.1. And after I finish this table, I'm going to show you guys where to find the e button on your calculator. So that means negative 1 comma 1.1 is on your graph. Okay, guys, let's plug in 0. Well, we know anything raised to the 0 is 1. Right, so e to the 0 is 1, so that's just going to be 3. So 0 comma 3 is on the graph. And our last value of x, 3e to the first, if I put that on my calculator, I get 8.2. So that means my value 1 comma 8.2, right about there. And notice, we know it's growth because it's got the swoop upwards. Okay, so you may be wondering where in the heck is this E button on my calculator? Well, if I want to find E, what I'm going to do on the calculator, I think calculators are universally this way. Find the LN button. There's a button that says LN. So what you're going to do is you're going to do second, which is a second function. Right above that ln, you're going to see a little e. You're going to do second ln, and then your calculator is going to say e to the something. And you can just put in whatever value you want. Right, whether it's -2 or -1, and then you press enter. So to get to that e, you're going to do second ln, and then it's going to say e with a little flashy thing there for you to enter the e value. So you can do that first if you want. You could just do 3 times second ln and then get the e to show up. Okay, guys, and we can work on this in class too if you need to, the calculator stuff. Okay, so what about this one? Y equals e to the negative 0.5x. Well, is that growth or decay? Well, in this case, we have nothing in front, so we can assume that's a 1. So, and we know our r is right here. So r equals negative 0.5 and a equals 1. So I can make the assumption that it's decay because r is less than 0 here. Okay, so I've strategically chosen these values so that they're going to multiply nicely. So if I want to plug in negative 4 for x, that would be y equals negative 0.5 times 4, right? So, sorry, negative 4. I'm sorry. Right, and negative 0.5 times negative 4 is 2. So my exact y value is going to be e squared on this one. So all I'm doing is making x these values. E squared, if you do that in your calculator, you get approximately 7.4. So that means the point negative 4, comma 7.4 is on my graph, right about there. Okay, now let's plug in e is negative 2. Well, I'm just going to erase this because I don't have a lot of room. If I plug in negative 2 for e, I get e to the first. And e to the first, we know, is 2.7. So that means negative 2, comma 2.7 is on my graph. Now I'm going to plug in 0. If I plug in 0, I get negative 0.5 times 0, which is 0. And that's just e to the 0, which we know anything to the 0 is 1. So 0, comma 1 is on my graph. And then last but not least, I'm going to plug in 2 for x, rather. Negative 0.5 times 2 is negative 1. So that's e to the negative 1, and that gives me 0.4. So that's about right here. So look what we get. We get our swoop down action here. Right, and notice, here's our y-intercept. So our y-intercept is when x is 0, right? And over here is also our y-intercept. Okay guys, I need these boards. I'm going to erase these boards and I'll come back with our grand finale in video 2.